The problem statement from GATE Physics 2013 paper reads as follows. A phosphorus doped silicon semiconductor whose doping density is 10 to the 17 per centimeter cube is heated from 100 degrees Celsius to 200 degrees Celsius. Which one of the following statements is correct? Option A. Position of Fermi level move towards conduction band. Option B. Position of dopant level moves towards conduction band. Option C. Position of Fermi level move towards middle of energy gap. Option D. Position of dopant level moves towards middle of energy gap. This is a multiple choice question with one correct option and we have to choose the correct one. Now, note that this is a phosphorus doped silicon semiconductor and we know phosphorus being a group 15 element will act as a donor in silicon. Silicon is a group 14 element, hence and the donors donate electrons. So what we are creating is essentially an n-type semiconductor due to phosphorus doping in silicon. Now, and it's heated from 100 degrees C to 200 degrees C, and we have to see what impact does it have on energy levels. We'll get to that. Now, on the top, you can see that this is a silicon lattice on which we have doped one phosphorus atom. In small orange circles, you can see that there are 5 electrons, and this extra electron is due to the phosphorus atom, which has an extra electron with it. Now, pay close attention. This scale is in temperature. This scale is in Kelvin. So we are required that it's heated from 100 to 200. So 100 degrees Celsius means we are somewhere here. So this is our initial point. I'm calling this as T initial. The question says initially we are at 100 degrees Celsius. So we are somewhere here. And finally we have to go 200 degrees Celsius, which is 473 Kelvin. So we want to reach somewhere here. That is T final, the final temperature that we want to reach. And you see this nature of curve. We'll try to understand why this is happening. First, let's go to below 100 Kelvin. Now, usually when we say that we have doped silicon lattice with phosphorus, we assume that it's automatically going to donate an electron, which is not the case. Note that this electron is loosely bounded to this phosphorus atom. At below 100 Kelvin, there is not sufficient energy that this electron is free, even though we have doped it. But this dopant is not contributing to the electronic charge, to the electronic concentration. Hence, we see very low electronic concentration. You see, this electronic concentration is very close to 0. So at this point, the electron concentration will be just Ni, the intrinsic concentration. So electronic concentration at this stage would be just N equal to Ni. However, above 100 Kelvin, what happens is that this electron gains sufficient thermal energy and it is freed from the Coulombic forces of this phosphorus atom, and this electron now becomes free electron, in this case by free electron above 100 Kelvin. This implies now this is free to conduct, and this implies it will form a part of conduction band. So its concentration, the concentration of electrons in conduction band will increase after 100 Kelvin, and this concentration will be exactly equal to Nd. So in this case, Nd was 10 to the power 17 per centimeter cube. So our concentration here at this stage it was Ni, N equal to Ni. In silicon, it's approximately 10 to the power 10 per centimeter cube. Right, but that's at 300 Kelvin. So let's ignore that. So it will be Ni, it will be very low. It will be very low. However, at this stage, concentration of electrons will be equal to the donor concentration, which is 10 to the power 17 per centimeter cube, and it will remain till here, right? However, you notice that at around 425, above 400 Kelvin, something happens. What happens is that now you see these electrons, these are covalent bond formed between two silicon atoms. Now this bond is vibrating. due to it also has a thermal energy. However, the temperature is so high that now these bonds start to break, and it will create a huge amount of electrons because there are so many amount of silicon atoms. So a huge amount of silicon bonds will start to break, and when bonds will break, they will contribute both. So these, when this bond breaks, both of these electrons will go to conduction band that will be free to conduct the current, and hence the concentration of electrons rises rapidly. You see, it's an exponential increase here. After certain time, at this stage, silicon bonds start to break. And note that now this lattice will forget it has a phosphorus dopant. Why? Because the concentration of electrons will be determined by how many silicon bonds are breaking, and hence this region is called an intrinsic region, because it does not depend on phosphorus or any kind of doping anymore. It just depends on the temperature, and it depends on how many silicon bonds are there, and that is intrinsic to the semiconductor. Now, this behavior, whatever I explained in terms of concentration of electrons, can be explained using an energy band diagram. So on top you see this EC. This is EC. This level is EC. This is EV. We saw that up until around 100 Kelvin. You see this. So the concentration at 100 Kelvin, almost all the donors have donated their electron. So Fermi level will lie somewhere between, this is the donor level ED, and this is EC. So Fermi level will lie this is the Fermi level here. This Fermi level will lie somewhere between the donor level ED and the conduction band level EC. However, as we continue to increase the temperature, we note that the lattice is behaving more and more intrinsic, and we know for an intrinsic semiconductor, the Fermi level lies very close to the conduction band. Very close to the energy band, very close to the middle of energy band gap. So this Eg by 2. So when we are moving in this direction, intrinsic behavior increases, and which we expect. We notice that due to the increase in temperature, more and more silicon bonds will break, and phosphorus or any other dopant will stop to play any significant role. The only thing that will play a role is the silicon bond energy, and which is due to the intrinsic nature of silicon. Hence, the lattice more and more will behave like an intrinsic semiconductor, and hence this Fermi level, as a function of temperature, you see it will start moving towards the center of energy band gap, right? So now what does it say? So now we are heating from 100 to 200. So what's happening is that the position of Fermi level is moving towards, look at option C, position of Fermi level move towards middle of energy gap. We saw this is the Fermi level curve, this thing. So Fermi level originally was somewhere between the donor level ED and the conduction band EC, near the middle of it. As the temperature increased, the intrinsic behavior of the semiconductor overpowered the extrinsic behavior of the semiconductor, and hence the Fermi level is moving closer to the middle of energy band gap, because that's where the Fermi level for an intrinsic semiconductor lies. Hence C is the correct option. Position of Fermi level move towards middle of energy gap. And note that the dopant level does not change. That does not change, because we at 100 Kelvin itself we have broken all the bonds. Thank you for listening.